The last section that we're going to do in Chapter 14 is called Spherical Coordinates. All right, so we've looked at rectangular coordinates, which you guys are very familiar with, x, y, z. We've looked at polar coordinates, where we changed two variables into the polar coordinates we were doing before. So we had cylindrical coordinates, I meant to say. And so now we're going to do spherical coordinates, and basically we're going to turn these into a sort of a three-dimensional version of polar coordinates. So we're going to have the r and the theta, okay? So that, or a version of r and theta. But we're going to have a third dimension as well that's going to be done using an angle measure. So we're going to have one distance measure and two angle measures. So what I'd like to do first is I'd like to pull in a picture, and this is just from your textbook, but I thought it was a pretty good one. Oh, hang on just a second. Oh, and you cannot see hardly anything. Okay, well, I'll try and draw over it in black and see if it'll work. All right, so you've got your three-dimensional axis here. Your value for your distance away is going to be sort of a three-dimensional version of what we call r. It's called rho. It looks like a p. Okay, when I draw it, I'll show it to you. But that's called rho. We're going to measure our angle theta right here. Okay, so angle theta is going to be on the xy plane. It's just how much around the xy plane you go. That's how we measured theta before. So theta is not any different. It's the only variable actually that stays the same. The variable that we're going to introduce that's different is one more angle measure, and that angle measure is coming down from the z-axis to wherever we are in three-dimensional space, and that angle is called phi or phi, depending on what you're using. Usually you hear mathematicians say phi, so I'm going to say phi. But there's no foes and fums, but yes, so I'm going to say phi because that's the one that you hear most often in mathematical circles, but if you say phi, it's okay, all right? So this is going to be measuring, and it's hard sometimes to remember where you're measuring it from, but you are measuring it from the z-axis coming down, okay? So keep that in mind as we're working. All right, so our measurements are going to be in rho, which sort of looks like a script P. We're going to measure in phi, and we're going to measure in theta. And depending on the textbook that you use will depend on how phi looks. So the phi that I'm going to draw looks like this. It doesn't look exactly like your textbook. Your textbook draws it looking like this, which is fine as well. So it's almost like a lowercase. It's a lowercase, uppercase kind of issue with the Greek alphabet. So that's what's going on with that one in the middle there. So that's phi. All right, so you need to know what the conversions are. I mean, just like when we did polar coordinates, how are we going to convert? Well, rho's the easiest one. So when we did r, it was, in fact, we wrote it as r squared equals x squared plus y squared, or some variation of that. So what do you think rho squared might be in three dimensions? It's three-dimensional distance. This is related to stuff we did in Calc 3. When we did distance in three dimensions, how did we find distance? We used, I mean, you're right, we used vectors, but when we were using vectors, do you remember the distance formula?
Square root of the squares.
Square root of the squares, exactly. So my rho, since I'm writing it as rho squared, is actually just going to be x squared plus y squared plus z squared. You guys remember that? I mean, it's not exactly what we did in Calc 3, but it's definitely related to the ideas of what we did in Calc 3 with distances. X is actually equal to rho sine of phi. Y is rho sine of phi. Oh, I'm sorry, I left that off. It's sine phi cosine phi. That's what happens. Cosine theta. When I stop reading my writing. Okay, and then the y is rho sine phi sine theta. Z is your easiest one. Z is rho cosine of phi. And it's sometimes helpful to be aware of the fact that r, that is like the r in cylindrical coordinates, r is equal to rho sine of phi. You may or may not find it useful in a particular problem, but if you find something with it that's already in cylindrical coordinates and you need to make a change or whatever, it'd be helpful to do that instead of to convert through the rectangular system. So that's another one that's in there too. So jot those down. You're going to keep flipping back and forth between those for the next 12 minutes, I guess, anyway, while the class is looking at these. All right, so the first thing we're going to do is like we did in section 14.6 is that we're just going to work on converting, what happens when we convert an equation, okay? So these are my list of conversions. You're going to have to help me as we go through them because they're not ones that I always have in front of my memory either. We're going to convert the spherical point rho phi theta into rectangular coordinates. And this is just an ordered triple. This is 2 pi over 4, 2 pi over 3. Okay, so this is not XYZ. We're going to find XYZ. This is rho phi theta currently. So how are we going to find X? Rho sine phi cosine theta. Good. And, oh, I said rho and I wrote R. Rho. Rho is equal to what? 2. Phi is equal to, and theta is equal to 2 pi over 3. And trig becomes quite useful again because we've got lots of trig going on in this problem, right? So what is the sine of pi over 4? Root 2 over 2, good. What is the cosine of 2 pi over 3? Unit circle trig. Man, is a killer, huh? Which quadrant are we in? We're in the third quadrant. This is one of those 30, 60, 90 angles, or right, 30, 60 angles, right? And it's the one that's closest to the y-axis. Yes? Cosine is the x distance. So this is the 1/2 value. And it's negative because we're in quadrant 2. And what I just talked through to you is exactly how I talk it through in my head when I think of it. Figure out which quadrant I'm in, figure out how far I am away. Am I looking at an x value if it's cosine? Am I looking at a y value if it's sine, and so forth. All right, so simplified, what does this give us? Negative square root 2 over 2. So that's x. How about y? Well, it's rho sine phi sine theta, right? So I have 2 sine pi over 4 sine 2 pi over 3. So part of this I already did. There's that square root 2 over 2 that Tally told us. How about the sine of 2 pi over 3 then?
Or no.
Root 3 over 2. And is it positive or negative? Do you know? It's positive because we're in quadrant 2, right? So what does this one end up giving us? Square root 6 over what? 2. All right, last one, z. Z is equal to rho cosine of phi. Rho is 2. Phi is pi over 4. So this is 2 times the square root of 2 over 2, which gives me square root of 2. So my ordered triple in the rectangular coordinate system would be negative square root 2 over 2, square root 6 over 2, and square root 2. This is just a glorified trig problem, right? That's really all this particular problem is. It's just some trig and unit circle stuff going on within the trig. Okay, we're going to do the conversion in the other way because that's actually a little bit more helpful for what we're going to be working on with integration, right? Taking rectangular and turning it into spherical. I'm not going to do it for a coordinate like an ordered triple. I'm going to do it for an equation in this one. So we're going to convert the equation to spherical coordinates. And the equation we're going to do is z equals the square root of 3 times x squared plus y squared. There's a couple of things that you could do at this point. You could change it into r first. Why might you want to do that? Because x squared plus y squared doesn't equal rho, right? I mean, so that's not exactly rho. That's not helpful. What if I didn't change it into r? What would I have to do? I'd have to square each of the cosines, the sine squared, cosine squareds with the rho. I mean, it'd be kind of messy, right? You guys with me? So this might actually be a helpful place for us to use the fact that we actually have r squared here instead. Because r is squared, we could actually write this then as r square root of 3. Now, I'm not where I need to be exactly yet, right? I mean, I've got r in it, and r is not in spherical coordinates. So what would I need to do then? Z equals rho sine phi. Oh, did I write the wrong one down? Hang on, no. I think I need sine. I was going to change my r next. I'm sorry. Maybe you guys were telling me what to change for z. Is that what you were telling me?
Yeah.
Okay, I was changing r. But yes, z needs to be changed as well. You're right. But r as well is going to have to be changed. Are you tracking with me? Okay. All right, let me go back over here. I was changing the other variable while you guys were changing that one. All right, so this would be, we can do both at the same time, though. How's that? So z is rho cosine of phi, and r is rho sine of phi, and square root of 3. So obviously rho could equal anything, agreed? I mean, there's no value particular for rho on this one. So, but we do have to have the cosine of phi equal to the sine of phi square root of 3. This actually solves for particular points. That doesn't always happen when you're solving an equation, right? When you're changing coordinates to an equation, but this one actually does. So rho can be anything. This is not helpful in particular if we were doing limits of integration because we need an upper and lower limit for rho generally. But on this particular one, we aren't doing a limit of integration, so that's all right. What phi values would this work for? Can you think through your trig enough to figure out when cosine of phi equals sine of phi square root 3? Thinking unit circle here, guys. Square root 3 should beckon you to think of certain angle measures, right? 30s and 60s, pi over 6s, pi over 3s. Which one is it? Which one do we want to have the square root of 3 in it? The sine or the cosine? The cosine, because we already have a square root of 3 on the side with the sine, right? So what we're wanting is we're wanting our cosine, we're wanting our cosine of phi to be one of these angles that gives me, something with a square root of 3 in it. We want it to be a square root of 3 over 2. I mean, that's what we want. Agreed? So where in the world is that going to happen? What angle measure does that happen for? Pi over 6. And so that's going to be a location and I need the signs to match, right? Sine and cosine have the same signs in quadrant 1 and in quadrant 3. So where in quadrant 3 would this work? what angle measurement in quadrant 3 is the same as this angle measurement? 7 pi over 6. So we actually end up getting two measurements, and this is, of course, within one circle. For what we're working with these coordinate systems, one time around the unit circle is plenty. If you wanted to be more specific, what you guys did in trig was something like this. Remember this? This is really every k pi over 6 because it's going to keep. Oh, k is an integer. It looks like kintiger actually, but yes.
Not learn that in kindergarten.
All right, so this will not always work out to being actual. We often end up with an equation here, not just a specific point. But on this one, we actually ended up with actual specific value coming out of it. All right. So let's see how this plays out, at least in setting up. I'm not sure if I can solve it. We'll see if we have time. The first problem. So this is example. We're going to set up and evaluate the indicated triple integral in an appropriate coordinate system. We have our triple integral over Q of the square root of x squared plus y squared plus z squared dv, where Q is bounded by the hemisphere z equals negative square root 9 minus x squared minus y squared, and the xy plane. So first issue, why is this spherical? Yeah, we've got all three of them squared, right? We've got an x squared plus y squared plus z squared, which this is then going to equal rho squared. And ours has actually got a square root in it too, so our integration on the inside is going to actually have rho. All right, so there's a note here that I'm going to write in at this point. Do you remember back in polar coordinates, we had to put r dz dr d theta. Did you hear I got it all in the right order that time? Didn't I? I did r dz dr d theta. We had this extra factor of r involved. Well, this kind of thing happens again here, but we've got more than just r involved. We actually end up with the r that we had before, squared times sine of phi, and then it's d rho, d phi, d theta. And if you'll notice right here, previously this had just said r, right? And what is r in this coordinate system? Yeah. So you get that sine of theta, and you're going to have another r involved. So there's some of that coming through to get this equation, all right? So we have r sine of theta, but it's r squared sine of sorry, not theta, sine of phi. All right, so as we're setting it up, we're going to need that as our dv on the end. All right, so taking a look at my limits of integration, we've just now changed this into rho, right? Square root of x squared plus y squared plus z squared is rho. And then the dv on the end is going to have r squared sine of phi I keep saying R, and I don't mean R. No wonder you guys are looking at me like I'm crazy. It's rho. I'm sorry. Rho squared, sine of phi. And then, yeah, that makes much more sense. D rho, d phi, d theta. So this is what I'm going to have on my function that I'm integrating.
So, like, rho cubed.
It will be rho cubed.
Okay.
Yes, it'll be rho cubed. You're right. All right, taking a look at the equations that I was given, let's try and get our limits of integration set up, and then I'll post the video that finishes the problem and the rest of it later. Taking a look at this right here, if I were to solve, or if I were to rewrite this, I would actually have z squared, and then if I square the other side, the negative is going to go away, and I can move the x squared and the y squared over to the left-hand side, leaving me with 9. So this is actually going to give me that rho equals what? Rho equals 3. And we're dealing with a hemisphere, so what is the other value going to be for rho? Hemisphere means half a sphere. Not -3. Remember, rho is a distance, first of all. 0, because we're talking about the distance from the origin out to the outermost edge of a sphere. Think of it like a ball, okay? So this is a solid object, starting with it, with density and mass and so forth. It starts at the origin 0 and it extends out to the edge of this surface, which is going to be r equal to 3, or rho equal to 3. What else do we have? Let's do the limits. Let's just go ahead in order. Let's do the limits of integration on on phi next. So do you remember how phi is measured?
It's from the z to
the positive z-axis down, right? But this is the hemisphere occurring where? Where does this hemisphere occur? It's bounded by the xy plane. So is it above the xy plane or below the xy plane? Below. Why is it below the xy plane? Yeah, that negative in front of the square root right there tells us that we are below the xy plane. So if we're below the xy plane and we're measuring from the z-axis, we don't actually start until we get down to the xy plane. How far have we gone in terms of theta? Pi over 2. And how far will we yet to go?
So,
even further than that, so it would be 3 pi over 2.
Nope.
pi total.
Pi. This is where it's hard to visualize, I think, too, is that you're measuring from the z-axis down. So from the z-axis to the x-axis, so to speak, is pi over 2. And then from the x-axis down would be the full pi. So we're going from the positive z-axis to the negative z-axis. Okay, we're not measuring x and y's, which is what you're thinking, Caleb. I can see it in your eyes. You're thinking positive x. You're thinking x and y axis. Yeah, but you're going from the z-axis.
No, I get that.
That's to pi over 2. And then it's another pi over 2 to measure from the x-axis down to the z-axis on the bottom.
Why are we stopping at the negative z-axis?
Oh, why are we stopping at the negative z-axis? Because our measurement only needs, because it's going to swing around like this to get the whole size, the other side of it.
Okay.
The other measurement, the d theta, is going to give us the circular part on the other part. Yeah. So we're going to go from pi over 2, whoops, to pi. And then the 0 to pi, the 2 pi is going to give us the full hemisphere that you were talking about to go around like this. So we're not spinning solids, but you have to have some sort of an imagery of what's happening. The theta is going around like this to get you the full circle, and then this measurement down here from the positive x-axis, or from the xy plane down to the negative z-axis, is going to give you the half of the ball, the hemisphere that you're looking for. Yes,
So
Nathan?
Because we're starting at pi over 2, that's the lower bound, and then since we're going with pi, that's the upper bound?
Yes, that's correct. Yeah, so when we're starting, and I wish I had, oh, no, I didn't get a picture of this, and I got a picture of a later one that I was going to show you guys. So we'll stop right here.